I want to walk through the practice test that's posted on Canvas. If you're not sure where to find this on Canvas, when you're at our home page on Canvas, there is a link. There's like these little blocks that say study, and it says preparing for tests. So if you click on that, it will take you to practice test, which is this test right here, and also the solutions are on there as well. But I want to walk through the solutions, kind of verbally describing where the answers are coming from. For the first problem, the molecule in the box, name any two functional groups except for alkane. So right here, there is an alkyne. Right here is an alcohol. This is an alkene. Here's another alcohol. This nitrogen is tricky. It is an amine. It is not an amide. An amide is a nitrogen that is attached to a carbon-oxygen double bond. And so that's just a really funny way of looking at an amine. Question number 2, which one of the following pharmaceuticals uses the molecule in the box as its active ingredient? So if you look back at that PowerPoint, I think it's the very first PowerPoint we did this whole quarter, this is a molecule that is used in female synthetic sex hormones, and we know that because it has this characteristic 4 rings kind of smushed together, plus the alkyne functional group. Those two things together are recognized as a synthetic female sex hormone. Question number 3, label the molecule that's definitely soluble in water. So the rules that we had for being soluble in water would be that it has less than 6 carbons, plus it needs to have at least 1 oxygen or 1 nitrogen. So less than 6 carbons and at least 1 oxygen or nitrogen. This guy on the right has 1, 2, 3, 4, 5, 6, 7. So this one right here is definitely going to be soluble in water. Second part of the question, label the molecule that's definitely soluble in organic solvent. So soluble in organic solvent would mean that it has no oxygens, no nitrogens, or lots of carbons. This molecule here has lots of carbons and also no oxygens, no nitrogen. So this is organic, soluble in organic solvents. Question number 4, this one is a topic that was based on the lab that we would normally do, but since we're not doing labs in person, that doesn't apply to us this quarter, so don't worry about that one. Question number 5, on this page, we're going to use this molecule in the box right here. How many carbon atoms and how many hydrogen atoms are in the molecule? So first we're going to find our carbons. Remember, the carbons are at the beginning and ending of every single line segment. So I'm drawing a dot at the beginning and ending of every single line segment, and then we're going to count up those carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. And then for counting hydrogens, I'm going to erase those dots. For counting the hydrogens, we have to remember that every carbon atom likes to have 4 bonds total. So we're looking at this guy right here. How many bonds can we see? We can see 1. That means that it has 3 bonds to hydrogen. Next carbon over, how many bonds can we see? We can see 2. So that means it has 2 more. The next one we can see 2, so it has 2 more. This one we can see 3, so that means it has 1 more. This one we can see 1 bond, so it has 3 more. Here we can see 2, so that means we can't see 2. The next one we can see 3, so it has 1 hydrogen. This guy has 3 hydrogens. That one has 2, and this last one has 3. And how many in total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. What is the best name for the molecule? Well, I made a mess all over it. Let's erase it. Best name for the molecule. So we need to find the longest continuous chain of carbon. So that means we can start at any ending. We could start here, 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 or here. And we need to connect any two dots that has the longest possible pathway. And I think that the longest pathway looks like this one right here, but we're going to check a couple other ones to see. So this pathway right here is 1, 2, 3, 4, 5, 6, 7, 8 carbons. I'm going to erase those numbers because they might not be that might not be numbering in the right order, but I just am doing that to count. So that was an 8 carbon path. Let's see if we can find a longer path. Maybe if we go straight from left to right. 1, 2, 3, 4, 5, 6, 7. Nope, that's not going to be it. So our longest path is right here. That's an 8 carbon path. And now we want to number that path starting at the end that is closest to our substituents or our branches. This end is closest to our first branch, which is right here. So we want to start numbering up here. That's 1, 2, 3, 4, 5, 6, 7, 8. 8 carbon chain, that means that this is an octane. Well, there's only one possible octane. So we didn't even need to really worry about all the numbering. But let's look at the numbering anyways. Our substituents are on carbon 3 and carbon 5, and they're both methyls. So we will say 3,5-dimethyl octane. What is the relationship between the molecule in the box and the molecule right here? How are they related to each other? Well, the first thing that we want to look at is their molecular formulas. Do they even have the same number of carbon atoms and hydrogen atoms? Because if they don't, that means they don't have a relationship at all. And we've already determined that the molecule in the box is C10H22. So let's check this guy down here. First, we'll count carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So far that's the same. Now let's count up its hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So they have the same molecular formula, which means they have some kind of relationship. There's some sort of relationship. So this E is not an option. So let's look at the rest of our choices. Cis-trans isomers is only possible when we have a double bond. And we don't have a double bond in these molecules, so that's not a possibility here. In enantiomers is only possible when we're using Fisher projections or when we're using wedge dash notation, and we can see something about the 3D shape. And we don't have Fisher projection or wedge dash notation, so that's not possible either. So our only options are they're either identical or they're constitutional isomers. To figure out if they are identical or constitutional isomers, we have to look at the longest parent chain. So the longest chain. And for the molecule in the box, our longest carbon chain had 8 carbons. So let's see if that's true down here as well. 1, 2, 3, 4, 5, 6, 7, 8. So that's the same. They match in terms of their longest chain. Now we want to look at the branches. Where are the branches? In the molecule in the box, our branches were on 3 and 5. Ooh, same thing. So this one has the same parent chain. It has the same branches on the same carbons. That means that they are just 2 different drawings of the exact same molecule.